The solar system, a vast expanse filled with planets, moons, asteroids, and comets, exhibits a fascinating characteristic: its flatness. This intriguing feature raises questions about the formation and structure of our cosmic neighborhood. At first glance, one might wonder why the solar system isn't a chaotic sphere filled with celestial bodies scattered in every direction. Instead, it resembles a flat disk with most planets orbiting the Sun in a relatively uniform plane. Understanding this phenomenon requires delving into the history of the solar system's formation and the fundamental forces at play during that process. To grasp why the solar system is flat, we must first explore its origins. Approximately 4.6 billion years ago, our solar system began as a giant cloud of gas and dust known as the solar nebula. This cloud was primarily composed of hydrogen and helium, with trace amounts of heavier elements. Over time, gravitational forces caused this nebula to collapse under its own weight, leading to the formation of a spinning disk. As the cloud contracted, it began to rotate due to the conservation of angular momentum, a principle that explains why objects in motion tend to stay in motion. This rotation caused the material within the nebula to flatten out into a disk shape, with most of the mass concentrated in the center, where the Sun would eventually ignite. Angular momentum plays a crucial role in the flatness of the solar system. As the solar nebula collapsed, it spun faster, similar to how a figure skater spins faster when pulling their arms in. This increase in rotation speed caused the material to spread out into a flat disk. The conservation of angular momentum ensures that as the nebula shrinks, it must rotate more quickly, leading to a disk-like structure. The centrifugal force generated by this rotation counteracts the gravitational pull, trying to collapse the material inward, resulting in a stable, flat configuration. This disk is where the planets, moons, and other celestial bodies would eventually form. Within this spinning disk, particles began to collide and stick together, forming larger bodies through a process known as accretion. Initially, tiny dust grains clumped together to create planetesimals, which are the building blocks of planets. As these planetesimals collided and merged, they grew larger, eventually forming protoplanets. The gravitational interactions between these growing bodies influenced their orbits, leading to a relatively flat arrangement. Most of the material in the disk remained in the same plane, which is why the planets orbit the Sun in a flat configuration. The gravitational pull of the Sun, combined with the conservation of angular momentum, helped maintain this orderly arrangement. Gravity is a key player in the solar system's flatness. As the protoplanets formed, their gravitational pull helped clear out debris in their orbits, leading to a more organized structure. However, collisions between these bodies also played a significant role. When two protoplanets collided, they could either merge or scatter, but the overall effect was to maintain the flatness of the disk. Over time, these interactions helped to stabilize the orbits of the planets, preventing them from drifting into chaotic three-dimensional paths. The result is a solar system where most planets, including Earth, follow a relatively flat orbital plane known as the ecliptic. The ecliptic plane is the imaginary flat surface that extends out from the Sun, encompassing the orbits of the planets. This plane is inclined at an angle of about 7.25 degrees to the Sun's equator, which is relatively small compared to the vastness of space. The significance of the ecliptic lies in its influence on the solar system's dynamics. It serves as a reference point for understanding the motions of celestial bodies, as well as for navigation and astronomical observations. The flatness of the solar system also allows for easier modeling of planetary orbits and interactions, making it simpler for scientists to study and predict the behavior of these celestial objects. In conclusion, the flatness of the solar system is a direct result of its formation from a rotating disk of gas and dust. The interplay of gravitational forces, angular momentum, and collisions among forming bodies created a stable, organized structure that we observe today. This flat configuration not only simplifies our understanding of planetary motion, but also highlights the harmonious nature of the solar system. As we continue to explore and study our cosmic neighborhood, the flatness of the solar system serves as a reminder of the intricate processes that shaped our celestial home. Understanding these processes not only deepens our appreciation for the universe, but also enhances our knowledge of the fundamental laws of physics that govern it.